So, what in the world could a 100-mile-per-hour fastball and the planet Mars possibly have in common? I know, it sounds like a riddle, but the answer is actually kind of mind-blowing. It turns out that everything in our universe, from a tiny baseball to a massive planet, plays by the exact same set of rules when it comes to motion. Let's break down how that's even possible.
Yeah, it's a strange comparison, right? One's a screaming projectile here on Earth, and the other is making this silent, epic journey millions of miles away. But the connection between them is absolutely real. They are both, in a way, speaking the same universal language of physics, a language that applies everywhere and to everything. So, to build that bridge from a fastball all the way to a planet, we've got to learn the lingo first. We need to get a handle on the language of motion. You know, physicists use just a few core ideas to describe any kind of movement, and these are the essential building blocks for everything we're about to get into.
All right, let's start with the absolute simplest concept, position. The easiest way to think about it is like a single frame in a movie. It's just an object's specific location at one specific moment in time. Where is it right now? That's its position. See? Simple enough?
Okay, so if position is just a snapshot, velocity is what's happening between the snapshots. Now, this is important. It's more than just how fast you're going. That's just speed. Velocity is how fast you're going and in what direction. So when you're driving, your speedometer tells you your speed, but your velocity is that speed plus the fact you're heading downtown. And here's that difference in action. A legendary fastball, right, might have a speed of 160 kilometers per hour. That's just a number, a scalar, but its velocity is 160 kilometers per hour towards home plate. That direction, that's the crucial little piece of info that makes it a vector. It's not just moving fast, it's moving fast with a purpose.
And finally, we get to the real engine of change in all of this, acceleration. And really, it's any change in velocity. So stepping on the gas, that's acceleration. Hitting the brakes, that's also acceleration, just in a negative direction. Heck, even just turning a corner at a constant speed is acceleration because you're changing your direction. It's the one part of motion you can actually feel in your gut.
Yeah, that feeling of getting pushed back into your seat when a car takes off, that's more than just a cool sensation. It's a fundamental force of change at work. So let's take a look at just how powerful acceleration can get, from stuff we see every day to things that are truly, well, mind-boggling.
Just look at these two extremes. When a jet lands, its velocity drops like a rock. That's a big negative acceleration. But on the flip side, when a drag racer launches off the line, it's a massive positive acceleration. So that little plus or minus sign, it just tells you which way the change is happening.
But if you want to talk about some serious acceleration, we gotta look to the natural world. Get this. When a rattlesnake strikes, its head rockets forward at 50 meters per second squared. That is 5 times the acceleration of gravity. It is an absolutely explosive biological missile launch. To try and wrap our heads around that number, let's put it in a context we can all understand. A car. If a high-performance sports car could accelerate like that rattlesnake, how long do you think it would take to go from 0 to 100 kilometers per hour? Well, the answer is just 0.55 seconds, not even a full second. It's practically teleportation. Now, there is one accelerator that we are all experiencing all the time, whether we're moving or standing perfectly still. It's that silent, relentless pull of the Earth itself, gravity. And when gravity gets to act on an object all by itself, we call that free fall. Down here, near the Earth's surface, if you can ignore air resistance, everything in free fall gets the exact same constant downward acceleration, 9.8 meters per second squared. It's so important it gets its own special name, g. It means that for every single second something falls, its downward speed increases by another 9.8 meters per second. It's like clockwork. Okay, so this leads us to a classic physics brain teaser, one that really stumps a lot of people. Picture this. You throw a ball straight up in the air. It goes up, slows down, hangs there for a split second at its peak, and then falls back down. So my question for you is, at that tiny instant at the very top, when its velocity is 0, is it still accelerating? And the answer is a huge, resounding yes. Think about it. Gravity doesn't just switch off for a second because the ball stopped. That constant downward pull, that negative 9.8 meters per second squared, it's there the entire time. It's what slows the ball down on the way up, and it's the very same force that speeds it up on the way down. Gravity never, ever takes a break. All right, so we've got the language of motion down. Let's go big. I mean, really big. Let's take these same ideas of position, velocity, and acceleration and apply them to the grandest stage we can imagine, our solar system. For centuries, people were just mystified by the weird paths planets took across the sky, until one man, Johannes Kepler, finally cracked the cosmic code. So before Kepler, the common wisdom, even from brilliant minds like Copernicus, was that planets moved in perfect circles at perfect constant speeds. It was a beautiful idea, but it was wrong. Kepler, after poring over years and years of super precise data, found out the truth was actually way more interesting. So Kepler's first law was a total game changer. He proved that orbits are not perfect circles. They're actually ellipses. You can think of them as slightly squashed circles. And the sun isn't right in the middle either. It's off to the side a bit, at one of two special points inside that ellipse called the foci.
His second law then explains how the planets move on these new elliptical paths. The technical description sounds a bit complicated, but the main takeaway is actually really simple. A planet's speed isn't constant. It moves fastest when it's closest to the sun in its orbit, and it moves slowest when it's farthest away.
And then we have his third law, the harmonic law. And this one is just pure mathematical poetry. It basically says that there's a beautiful, precise relationship between how long it takes a planet to orbit the sun, that's its period, and its average distance from the sun. It's a hidden rule that connects the whole solar system. And the best part is, Kepler didn't just dream this up. He had the receipts. Just look at this table. It's his actual data. Now look all the way over at that last column. You take any planet's distance cubed, divide it by its orbital time squared, and what do you get? Pretty much the exact same number every single time, from Mercury all the way out to Jupiter. This was the cosmic fingerprint. This is how he knew he was onto something huge. So Kepler gave us the what. He drew the perfect blueprint for how the planets move, but he never knew why. That incredible discovery would have to wait for one of the greatest scientific minds ever, Isaac Newton, the man who would finally connect a falling apple here on Earth to the moon orbiting in the sky. This was the ultimate question, right? It's one thing to see a pattern, to describe it perfectly with math, but it's another thing entirely to understand why that pattern exists. Why ellipses? Why does a planet speed up and slow down in exactly that way? There had to be a deeper, more fundamental reason for all this celestial clockwork. And this is where Newton's genius just shines. He connected all the dots. First, he started with the basics. A planet is constantly changing direction in its orbit, so it has to be accelerating. Second, he did the heavy-duty math and figured out that this acceleration is always pointed directly at the sun. That means some kind of force must be pulling the planets toward the sun. And then the legendary light bulb moment. He realized this force was the exact same thing that makes an apple fall from a tree or that makes a fastball curve towards home plate. It was gravity, a single universal force tying everything together. And just like that, the mystery was solved. Those simple rules of position, velocity, and acceleration that we use to describe a fastball are the very same rules that, when combined with gravity, explain the majestic dance of the planets. It all fits together perfectly. It really makes you wonder, doesn't it? What other elegant universal rules are out there, running the whole show, just waiting for us to discover them?